Welcome to day 66, chemistry fans, and this would normally be our solutions test day, but of course you'll be taking your remote assessment this week. Our target at the beginning of this would be to understand how solutes can impact the freezing and boiling points of solutions. That, of course, in a more complex way is the story of this poor frozen froggy, who's not actually dead because he's used the miracle of chemistry to stay partially animated. So I'm going to get rid of my big head, and you are going to write down these wonderful questions. The first of those, of course, would be drawing and explaining microscopically why people do weird things like spray salt all over icy roads. And then which of the following would impact the boiling point of water the most? 2 moles of calcium chloride or 2 moles of lithium chloride? Or 4 moles of glucose and 3 moles of sodium fluoride? So write down the questions, take your best stab at it, make sure you draw and explain because you know that builds your brain even though you hate doing it. And then we'll go back at it together in right now. But pause me so you can actually think about it and build your brain. Now, key thing we should notice, of course, is all over that road is this stuff. It's called water ice, right? Solid water is in its ice form. And one thing we should notice about it is everybody says that every snowflake is special and different. That is a bold-faced lie. If we look at snowflakes, they are very, very beautiful and can have little differences, but at the core of them, they're all made of the same thing. They're made of water, and that's why they all have this lovely shape right in the middle. It's six-sided. It's called a hexagon. Now, that is because as water chills down, the water molecules move slower. And being Mickey Mouse, his chin is negative, his ears are positive. And other waters are also polar, and they have charges as well. So that means that anytime you do that, the negative parts of one Mickey are attracted to the positive parts of another, and they form these temporary bonds. They're attractions, but they're a form of weak bond. That's essential to most things in science. And they are creatively named after the ear, which is a hydrogen, attached to the negative thing, and that is called a hydrogen bond. I always tell people in AP Bio, when in doubt, hydrogen bond, because they basically make everything possible. You can hold together your DNA. So water attracting to water is formed by a hydrogen bond. As this does this enough, you can get enough waters that if you look at their shape, being little bent molecules, they can each attract to each other. And as they attract to each other, they arrange themselves in the shape of a hexagon. The positives attracting to the negatives attracting to the positives. So you end up with this beautiful structure that is always a hexagon. And if you build hexagons upon hexagons, you eventually get an ice crystal, which is a snowflake. Now, the thing that we should notice is they get close to each other because opposites attract. But at the same time, they can only get so close to each other because they both also have negatives and they both have positives. And that means that as they get close, around 4 degrees Celsius, they get as close as they can get, as dense as water can get. And then as they approach closer, then those like charges can start to repel. And what they do, of course, is they push each other out. So these like charges of the negatives and positive repel each other out. And the perfect shape and size to do that is a little microscopic hexagon that allows them to be as close as they can be and as far away as they can be with the charges in balance, right? So notice that this is held together. This is a crystal lattice. That's why any crystal you step on it fractures because the bonds are attracting them by their charges. Now that ice crystal, of course, can have a little melted water on top of it, which makes it very, very slick. Now, problem is, of course, you don't want your car slipping on that. So what do? Well, in New York, where I'm from, they spread salt all over it because they don't care about salmon. And when they do that, of course, you throw that down in little crystal lattices. So you add salt to this thing. As you add the salt, we hopefully know by now, is when you add salt crystals into water, the water will rip apart the salt. Well, likewise, the water has charges, the salt has charges, and opposites attract. And as they attract, they then rip apart the crystal lattice of the water, right? So the cool thing is they can rip each other apart, and then they can rearrange themselves as you dissociate, so to speak, the water crystal with the salt crystal, and you end up with this magical stuff called salt water, right? And the salt water, of course, is because the waters have now been kidnapped, so to speak, by the ions, and now they surround them with their opposites attracting to each other as they form this dissociated complex, which we now would call salt water. The pen's going to freak out. Now, as it does that, we've got our little kidnappings going on. They are stuck in the parking lot spaces that we've been talking about throughout this unit, and we've created this great thing called salt water. Now, why do they do that? Well, one thing is for sure, this is going to help to rip apart the ice crystals that are making the road slippery, so you get a bunch of salt water on the road. But the awesome thing about that is, now that the water is attracted to those ions, the water can't form easily the hydrogen bonds to form a crystal lattice. So since they can't form their own crystal lattice, which we'd call ice, they can't freeze easily, which means that this salt water will stay on the road. It won't freeze and make ice that's slippery. So the cool thing is it prevents the ice from forming. What we call this freezing point depression. Basically, it would have to get really, really cold enough to force out those ions to form ice out of the salt water. And that's why in the high Arctic, it has to be the coldest part of the year before you start getting sea ice to form, because it has to push these salt ions out of the way. But as salt water, that causes the freezing point to decrease. It has to be colder and colder to do it, because basically the ions are holding the water into a solution. So it can't escape it and become ice crystal, which is what it wants to, right? Now, at the same point, if you were to increase the temperature, right, make it warmer and warmer and warmer, these extra charges would also hold on to the water. And what that does is that does the opposite. That's called boiling point elevation, which means it'd be harder to boil off the water because it's attracted to the salt. But that's a great trick that you can use when you're doing things like cooking. This is also why the ocean doesn't freeze when it gets really cold in, say, the up near Alaska. Even though it's really cold, like below freezing, it still will stay in a solution because the salt is there holding it. It's also why it doesn't totally evaporate all of a sudden, because the salt is holding it together. Now, this has anything to do with real life. It's just how, the ocean doesn't evaporate or freeze up and all of life can exist. Chemistry. So if we look at this, of course, you can predict this stuff if you just take them and you try to boil them in water. So what we should do is, of course, look at this first one. We got 2 moles of calcium chloride and 2 moles of lithium chloride. I'm going to make 2 beakers, right? My solvent is going to be water. And if I throw 2 moles of calcium chloride in one versus 2 moles of lithium chloride in the other, well, those are both ionic substances. And being ionic substances, and they both, of course, are soluble ionic substances, they're going to dissociate. Now, the 2 moles of calcium chloride means that the calcium ions are going to dissociate from this, and you're going to get 1 calcium ion and 2 chlorine ions for every calcium chloride. But I had 2 piles of this stuff. So I'm going to end up with double the amount, 2 piles of that and 4 piles of the chlorine ions. What I end up with total is 6 ions in solution, and of course the waters are surrounding those things, holding them in that solution. At the other side of that, I got 2 moles of lithium chloride, and lithium chloride, of course, is diatomic, and it's got lithium and chlorine popping off making 2 ions, but I have 2 piles of it, so that means that I'm going to have double that amount, so that's a total of 4 ions. Now, if you compare the 2 of those, one thing we can see is this one right here, the calcium chloride, has more ions in it, and that means it's got more things to hold on to water. It's going to have a greater impact on the boiling point. It's going to elevate the boiling point more. It's also going to depress the freezing point even further, and this is what we call boiling point elevation or freezing point depression. This solution will be harder to boil because it's got more ions holding the water in the solution. Likewise, calcium chloride would make the freezing point even lower because it's got more ions to, of course, split up the water and hold it in solution. That's why it's known as de-icer. This is what people spray into their locks or sprinkle on their driveways when they're doing that, right? Also, I could try a different substance. I could use this stuff called glucose or toothpaste, sodium fluoride. So if I try that, I'm going to have 2 beakers again. And when I look at these 2, of course, here I got my 4 moles of glucose, and I got my 3 moles of toothpaste, sodium fluoride. If I stake these and I throw these into solution, the thing that I should notice is, hey, I got 4 piles of this and only 3 piles of that. It should, of course, go with the more piles. But we have to remember that glucose is not an ionic compound. It is a polar molecule, which means it's going to like water and it's going to dissolve, but it's not going to dissociate, which means that overall it's going to make 4 particles in solution that hold on to the water. Likewise, the sodium fluoride is an ionic compound. It likes water, but it also dissociates. So that's going to make, for each one of those, 2 particles, but there are 3 piles, so that's 6 particles total. And that means that I was just looking at this. This one has 6 particles. This one has 4 particles. Which one has more particles? Well, the sodium fluoride has more particles. That means that it's going to have a greater impact on the boiling point. So it would boil at a higher temperature. It would also freeze at a lower temperature. Even though this one has more piles, it's the fact that this dissolves, so it doesn't dissociate into more particles, and this dissociates. But that's just another reason why we stress dissociates versus dissolves so much, right? Now, how would you use stuff like this? More particles, more dissolved particles in solution could cause the boiling point and freezing point to change more. Well, we use it all the time in life. Let's say that you want to make old school ice cream. You throw your fatty cream, you throw your sugar inside of this inner part of the ice cream maker, but on the outside, you actually put water with salt and ice. And you put the salt in there because that means that the water can allow it to get colder than the freezing point of water as you turn it around, which makes little tiny, very finely formed ice crystals inside of your ice cream part of it. That's because you've just decreased its freezing point. You've made it colder than it would be by adding the salt to it, kind of like the ocean. Or let's say that grandma is like making some spaghetti and she puts the water in and then she sprinkles some salt into the water as she gets it to boil. Why does she do that? Grandma might not know. Maybe she does. Maybe she's a chemist. Maybe she's just doing what her mommy used to do or her grandma used to do. But the key thing is as you add the salt to the water, it can now boil at a higher temperature. Then you throw in your noodles and they cook faster because now the water is higher than 100 degrees Celsius. You've increased its boiling point by adding the salt ions in there. Or the story of this poor frog. He lives in a cold place like the northern reaches of Canada or New York, where I grew up. And one of the things that we can see of that is he looks like he's frozen solid. But the cool thing is what he did was he released a whole bunch of glucose, sugar, into his blood. He increased his blood sugar concentration. By adding more sugar into his blood, he prevented ice crystals from forming inside of his body, just like on the road. And that prevented these ice crystals that are on the outside from forming and cutting through things like his brain and his kidneys and his heart. And then when summer comes, of course, he's still in a solution form inside, didn't form ice crystals. He thaws out and goes back to solution form and then hides that back inside of his liver as glycogen. It's almost like chemistry makes ice cream, frogs, and spaghetti, all kinds of good things to eat possible. Yeah, frogs are good too. Now, cool thing is you'd be taking the test normally. You're going to get yourself a nice remote solutions test. I would suggest that you go through and do the review first. I'll provide for you the review answers for that. Then you're going to submit your answers. Some of them require you to type it in. Some of you require you to take a picture and then submit it on that solutions document. So make us proud, people. We've done 3 remote weeks of this. This is the 4th week of it. Piece of cake. Hopefully you notice you can use your notes, your ETDs, and all your form assignments to try to figure out what those things are and show us that you know what you're doing. Good luck. Make us proud.